issues that we want to get hold of as soon as possible. So one thing is that some of you already saw the message from Chancellor. So the campus is going to open soon. I don't know. I think like there is a lot of confusion around things, but maybe this might be a good just to get a sense of how many of you, are not concerned about getting back to lectures in person. And if any of you have some concerns, like what are your concerns? You can unmute yourself if you want to speak up. Is everyone around UCSP and you're kind of like ready or like will be around UCSP? I think like February 1st, right, is when things are going back to normal. Okay, so some of you are driving back, some of you are already back, and none of you have any concerns about getting back, right? So I'm guessing that like all of you are most of you are waiting. Like I'm not assuming, but like it is possible that most of you are excited about getting back in person. I'm personally excited. So but I also don't want to make it painful for students who don't really want to come in person, right? It's a time of uncertainty, but we'll see. Any other comments? Any big concerns about getting back to class? So this is a good question. Will future in-person classes be recorded? I think they should be recorded. Since I didn't teach in fall, so I don't know what exact, like, I need to figure out what exact, tools people use to record the in-person lectures, but I'm betting it's not going to be very, rocket science thing to figure out. So we can figure it out. I guess the message is that we should be recording those in-person lectures. So that like, some of you who are not able to make it for various reasons are able to catch up. So, I'll make sure that we record those classes. Okay. So I hear a lot of you are already planning to be back. Anybody else who has, a counter opinion on this about getting back, coming to UCSP? I'm trying to get a sense of, like how many students I'm going to expect in person versus how many students are going to attend the lectures online or recorded lectures, basically. All right, so I'm looking at messages and I don't hear any counter voice. So it seems like I'm assuming everybody is excited. The quizzes will still be online. So, quizzes will not be in person. The midterm exam, I think I'll keep it online unless, like you all want it to be in person. It will keep things simple. We'll use the, like the lecture time day to keep it online. I'll try to design it in a way that, like you can have flexible hours to work on it rather than, like be crammed to sit here and give the exam. It will be an open book. So I don't think I'm worried that, you will open your lecture slides and open something else and then answer the questions. I think like that's not really what I'm going to, that's not what I'm trying to test here. I think what I'm trying to test is like how much of these basic fundamentals that we're trying to cover here are clear and how well we can answer those basic questions, right? And if you have already participated in the quiz questions, I think you get a sense of what needs to be done. That they're not rocket science questions, but I guess they test your clarity on fundamentals here, right? And that's what you should expect the midterm exam to be. But it will have a few more questions related to the discussion section, which I'm going to talk about soon. But yeah, that's kind of like going to be the format for the midterm exam. I haven't really written down the exam yet, but I would expect that it should be finished or it should be doable in a couple of hours, and you'll have flexible hours to work on it. All right, so I think another like topic that we should discuss is the discussion section. So unfortunately, they haven't gone as planned for various reasons, and I think the two students, they are also my graduate research students, and they went to their home country for various personal reasons. But each of them are struggling. Either they are struggling to come back, or they contacted COVID back there. So it has been a real struggle for them to stay connected and stay on top of everything. And also there was some confusion about the timings, right? So I think this I would blame on the admins about the communication to the faculty. I was talking to some students last week, and I realized that the expectation is that each of you have signed up for 3 different discussion sections, and then it appeared like only one happened. So other students kind of missed out on joining the discussion section, and then the session was not recorded. So now the video is available, but I think a lot of you didn't get a chance to look into it sooner, right? But I think the assignment 1, it's supposed to get released today. It's in final stage of testing before we can release it. But yeah, I think so even though we have missed the discussion section 1 and discussion section 2, most of you have missed it. But I think they are there, the videos are there, and there were some cover-up sessions as well. But the next set of sections, discussion sections, are going to be more critical as we move forward. So what we will be doing is that we will be falling back to those 3 slots that you have, and based on whoever signed up on each of those 3 slots, we will proceed accordingly. The challenge is that a lot of you don't show up in the discussion section. So I would encourage all of you to at least show up for one of the 3 discussion sections that are there, right? Or whatever you signed up for. It will be helpful because the way we are going to run these discussion sections is a bit tutorial style. So we'll cover some basic concepts, but we will also try to use running examples to make you understand how different pieces are working. And I would say that that's going to be very critical for you to be prepared attempting all the questions or all the challenges that we have for the programming assignments, right? So the lectures won't really directly cover the programming assignment related stuff as much. The lectures are going to cover a bit more on the broader set of fundamental challenges that we have. The discussion section will be a bit more low level detail, so that they will prepare you to approach the programming assignments better, right? So please make your best attempt to join the discussion section. But there has been a lot of chaos so far. I'm hoping that things will settle down soon, and we will have these discussion sections on a much more regular basis. Any questions about discussion section before we move forward? No? Okay. Also, any questions about quiz 2? I think the due date is still not on, so I think maybe we should not discuss the answers, but any other, I think there was some problem that maybe Austin, you pointed out, and I think Garrett pointed out, but I think that has been fixed. But somebody was saying it has not been fixed. I'll double check, but I tried to fix it as soon as possible, but maybe that didn't get reflected. Okay, all right. I think this is all I had about the logistics. If you have any questions or concerns, just let me know. And also, I will encourage you to show up for the office hours, especially the one that I hold on Friday, if you have any specific questions or concerns about how we are making progress, right? So keep in mind that this is something which is a bit of a challenging course because there are a lot of moving parts. I don't know if anybody is offering such a course at undergrad level, but at the same time, given the value that this area has, this topic has, I'm trying to make it work for undergrads, but there's still a lot of moving parts, right? So if you have any confusions about how things are going, and if you have some suggestions and feedback on how we can improve things, just let me know. Don't feel shy that you cannot or you don't have the channel to me. Feel free to communicate. I'm all here to get your feedback on these things. Okay. All right, let's get started with the lecture. So can you see my screen? So I think in the last lecture, we were talking about Onyx, and we kind of at the tail end of the lecture, there were a few topics that we had to run through, and maybe that was not making it easy to understand the key concepts in this topic. So I thought that maybe we should, revisit some of the key questions and make sure that we thoroughly understand the challenges of designing such a distributed operating system or network operating system in this context. Okay, so anybody wants to tell me about the Onyx? Like, what did you learn about Onyx? Like, what are the biggest takeaway from Onyx from last lecture? Is that something which is like just a research artifact, or is that something a bit more real? Maybe that's a very startup question. Okay, so the question that I had was that, is this some academic research prototype, or is that something which is like more production? So this is a research, like this is a research idea that got transcended into a production system. So the Onyx, even if I have the reference to the Onyx paper in the website, and Onyx paper was basically a summary of design choices that the practitioners made to make it work in a production network. And most of them were, like practitioners at Google, who were trying to make Onyx work as a network operating system within their network, right? And I'm opening this specific slide because I want us to have this full picture clear about how Onyx really works. So Onyx has these setup where we are trying to like provide this logical centralized abstraction, but at the same time, like physically it is distributed across multiple instances which are directly connected through a subset of switches, right? So now the question is like, why, and maybe this is a bit of a repeat from the last lecture, but the question is why, or what is the value of connecting or dividing this setup across multiple instances, right? So why can't we have just one big server? Why do we need multiple instances to enable a network operating system? Stress on channels, yes. So what do we mean by stress on channels? Let's try, like, we covered this in the last lecture, but I want to make sure that we get to the basics here, because it's important to understand the design choices that practitioners made here, right? So what do we understand by stress on channels? Is this the stress on the switch side, or is this the stress on the server side? Yes, yes. So let me quickly try to share. All right. So I think what I'm arguing is that we have this one big server, right? And then we have a network of multiple switches. Okay, they're all connected with each other. And this is, so when we have this, like connection of switches or routers, what do we call this? What is this called? So this is called network topology, right? So we have a topology of network here, which is representation of like, all these networks like this. So we have, I have a very simple setup here that we have this topology with for 6 switches or six routers, right? So if I am trying to connect all of them to one server, then I have to have a dedicated channel between all these switches and this server, right? So I'm marking this as basically, the physical network interface that the switch will have, right? And maybe for 6 switches, the overhead will not be super high, right? And now you might be thinking that what really is the overhead here, right? What is the information that is communicated between the switch and the server and vice versa? So can anybody give me a sense of, what do you think is the information that is disseminated between switches and servers? Okay, match action table. So you mean, so Steven is saying match action table. Basically, like another way of thinking of it, like from forwarding abstraction perspective, what we're talking about is a forwarding state, right? So we want to update the forwarding state in the switch, and that is one set of communication between the server and the switch, right? So this is kind of like a downstream information flow. But what is the information that can go up from the switch to the server? What information can go from switch to the server? Okay, so there can be events like node failure. So maybe, like this this link goes down, right? So the switch will have to update that this link has gone down, which means that now we have to operate on a different network topology. Now trunks messages that packet that does not match any field in the match action table, right? So that is something that we have already like discussed in the past, that the most common practice is that when you don't have or when a particular packet does not match any of the rules in these match action table entries, then they are handled by the controller itself, right? So which means that like if we assume that the switch basically started with a state where it had no rules in the match action table, right? Then every time a flow which is coming in, it will send an update to the controller. Now controller will say like, okay, I know where this flow has to be forwarded, and it will push a rule down in the switch, right? So like a flow will be basically packets, bunch of packets that share the same header fields with each other, right? Now this first packet comes into the switch. It does not find any match action table which it can match to. Then this first packet will go to the controller, right? And controller will have to implement logic on how to handle this packet. And it can decide to send it on a default port. It can decide to send it on like different like a specific port. So assuming that controller knows how to handle this, it sends a match action rule here, and it sends the packet back as well. So it sends the packet back, and it sends the match action rule, which is now installed in the match action table in the switch, right? So now this is the first packet. Now the second packet, when it comes in, then it will actually match on this rule, and then it will go forward, right? So either on this port or this port, right? Clear? So basically now we are saying that whenever a new packet for a particular flow comes in, and if there is no existing entry, then it has to go up, right? Or in the worst case, every time a new flow is coming in, then at least the first packet of that flow has to go up to the controller and figure out what the forwarding decision is for that flow, right? So that is already a lot of packets or a lot of communication that is between the switch and the controller, right? Because there can be a lot of flows that can get spent because like flows, they don't last long, right? So think of a flow when you're trying to do any type of web browsing or something, then you are trying to start like you're trying to create those TCP connections. First you send like from the application layer, you send that HTTP request that gets like translated or converted into a TCP packet, and then gets into the wire. But before this all can happen, the two end hosts have to establish a TCP connection between each other, and then only they can start sending packets between each other, right? So and that is one flow or one TCP transport session that is created for one type of activity, or like one event for HTTP browsing, right? So in general, like when you think of web browsing, the duration of these flows is relatively short-lived. But even in the data center networks, where I have so the data center networks are basically a lot of time responding to the type of requests you have, right? So depending on the type of workloads that are out there, a lot of time these workloads have or require short-lived flows. They don't require, like very long, sessions of data transfer. It's usually bursty, that you create a connection, you send some data, and then you disconnect, you terminate that session, right? And then later when you have something more, then you create another session, send more data, and terminate, right? So in most cases, the flows are relatively short-lived. They are bursty. So what that translates to is that, like the number of new flows that will come into these type of networks is, very close to the, or is very close to the, like order of number of packets coming in, right? So if a network is handling billions of packets, there might be few tens of millions of new flows associated with that packet, right? So that is actually a very intense workload. Maybe I'm exaggerating here, that like maybe it's not 10 million, it's like 1 million, but 1 million events here is also a lot of load from one switch, right? And then when we have a network where we have so many switches out there, then overall the workload in this case, the capacity between, like the network capacity of the switch will get easily exhausted if we have a really massive network to worry about, right? So the key idea that the Onyx had was that, okay, let's have this, like breakdown of this, like the network operating system. Let's divide that into multiple instances, right? And so what that does is that now we have these, like we have the same topology. Oh, maybe I had 4, yeah. Okay. Okay, so now maybe it will say that, okay, let's have 2 instances of Onyx, and like these 3 switches will talk to instance 1, and these 3 switches will talk to instance 2. Okay, so adding basically one more, like one more instance in this case, I have half the workload for an individual instance, right? Now the challenge is that, what about the control programs, right? So if I am writing a control program that is running on this instance, so it needs, it cannot, or it need not operate on a partial view of the network, right? So in a sense that, like this is the instance. Within that instance, we have some modules that are responsible for, like importing information from the switches, and then they're responsible for, like importing and exporting information across different instances, right? So this interface between the switches and the controller, that is southbound, right? And the interface between these 2 different instances is east or westbound interface, right? So these are very basic principles of network operating systems in general. So now, these interfaces are providing these instances to import information from the switches, or import information from the other Onyx instances, and also export the information, right? So if they want to push something out into the network, they can actually, like write rules or update the information that will get pushed down as open flow rules, right? And each of these instances will have a network information base. Right. And then the control program will be using this, will be using the API between the nib, like offered by the nib, to basically, enable flexible network control or whatever control they want to enable, right? So now I think because these nibs are maintained across 2 different instances, then that intrinsically leads to the requirement of, consistent view, right? So the control program here, control program 1, control program 2. So both of them need a consistent view of the network, which means that they not only have to import the information, the stateful information that is coming from these switches, but they indirectly have to also get the information from the set of switches that are under the controller, or like instance 2, and that information has to be imported from here, right? So this is like, this is something that we were trying to cover in the previous lecture as well, that why do we need this type of, like information exchange, right? Like, why do we need any type of replication of information across different instances? Because each of them, if without any replication of information, without any exchange of information, like each of those instances will have a partial view of the network, right? And we, like a control program, you don't really want a control program to just operate on a partial view. So you want this type of information to be exchanged with each other, right? Now, I think like in the last lecture, we also talked something about the state, like, the different types of state and different type of requirements that they have in terms of, storage and information exchange, right? So, we can actually divide, maybe, so you can see my screen. Yeah. So we can actually divide like this information on in two broad categories, right? Or like we can divide this type of state information into broad categories, depending on their requirements of how fast they are changing. And, like if they have any type of consistency requirements that they have to be consistent whenever a program is actually accessing that information, right? So like, I think like, let's try to understand two instances of that information, and that way we can appreciate that, like why it is okay to have different set of requirements from that, right? What Onyx was arguing is that not all network state is the same, right? So some type of network states require like really fast read and write capabilities, and they don't have a very strict consistency requirements. When I say consistency requirement, meaning that the consistent view across different control programs, right? So, one control program might have a different view, the other control program might have a other view of a particular state, and it does not make as big of a difference compared to some other states which really need to be consistent, right? And the consistent state requirements are the ones which, like are slow changing states in the network, right? So now I just elaborated this example a bit. Now the question for you is that, can you give me an example of a network state that is changing very fast or versus a network state that is, like changing slowly? Give it a try. Well, what do you think is a network state that will, change very rapidly?
Can you repeat the question again? Sorry.
Question is that, we talk like Onyx talks about network state, right? So it is like, every entity in the nib has some state associated with it, right? So the question is like, can you give me an example of network state that is changing rapidly? So let me give you some intuition for the changing network state, right? So in general, what is the most dynamic thing that is out there in the network? So the like when we talk about the networks, the most dynamic thing is anything that is affected by each and every packet coming into the network, right? So think about the states such as counters, right? So we are trying to maintain counters for each and every port, right? So that counter is going to get updated whenever a new packet comes in, right? And now when we know that, packets can come as fast as billions of packets per second, right? So that is an example of a very dynamic state. So like, I think congestion is dynamic, but I think it's a bit derived state in some sense. What I'm talking about is a state that is accessible via the Onyx, and Onyx can register itself to, like listen to certain set of states here. And an example of that state is the counters associated with the network entity, right? A network entity here can be a port, it can be a switch, a host. So, like any counter associated with that will be something that will vary as fast as the packets coming in, right? And like, as we know that the number of packets coming in can be extremely high, that means that the state variable associated, here with which has to do anything with packets will be very dynamic. Is this point clear? Yes. Okay. Good. Good. So now I think, like, anything that has to do with packets is something that's going to change very fast. What is an example of things that are going to change relatively slowly? So I'll try to build some intuition there, right? So, like, something that will change very slowly. A good example of that is the change in the network topology itself, right? Say, for example, a particular link goes down, a particular switch goes down, right? So the state which is associated with, which is, like, which is saying whether these devices are active or not, or live or not. So that is a state which I can say is relatively slow changing, right? Right? Does everyone agree with that argument? Yes. So I think, like, these are two extremes, right? Things that happen very rarely, right? That is also part of network state that Onyx nib is interested in. And there are things that are changing extremely rapidly, and those are also part of the Onyx network state, right? So I think, like, that, we cannot come up with just one solution that works for all types of network state that are, like, embodied as part of nibs, right? So that is why the Onyx actually came up with these, like, two different features or two different support for maintaining the, or two different storage support for maintaining state, right? And so, yeah, so you can't see my slides right now, right? So in the last lecture, we mentioned something about replicated transactions, storage, that is, like, SQL-like replicated transactions, and one-hop memory-based DHT, right? So, like, for the state that are changing rapidly, it is providing a storage, like, here you can imagine it is providing a storage, like, one that can change very rapidly, right? So, like, if the information that is coming in here is about the number of packets which is getting, like, every time a new packet comes in, a new, like, this counter has to be updated. So that is something which has to be stored in some type of storage which is changing very fast, right? Or which can support a very high read rate or be very high write rate, right? So this is this is very different from the requirements where we want like consistent view, and that view has to be replicated across all instances here, right? So if like there is some type of inconsistency between what controller 1 or control program 1 knows versus what control program 2 knows about the number of packets, it won't have as severe of an impact, right? But if control program 1 say is not aware that this link is down, and control program 2 is aware of that link is down, then that is not a desirable like operating state, right? Because your one control program is completely unaware of the state of the network topology itself, right? So like that is a state that has to be very consistently replicated across different instances, and that is a very different type of requirement. And what Onyx did was that it leveraged some of these existing like distributed storage systems out there, which provide like consistent replication of information across different instances. And the underlying principle there is that you can provide consistency, but providing that consistency comes at the cost of like the communication overhead about how much information needs to be exchanged between different instances to have a consistent view, and also about speed, right? So they like, having a consistent view of the network is not going to be very fast, right? But that works out in the favor of these network operating system in general, because like we don't really need consistent state for a fast changing state. We need a consistent state for the type of network state that are changing slowly, right? So that is kind of like a natural advantage that we have in here when it comes to storage. And like that is the natural distinction that the Onyx also made, that we can treat these different type of network states differently. We can come up with different type of abstractions or storage services for exchanging this information or storing this information and sharing that across different instances. Okay. Any confusion so far about this type of design choice? Okay, I think that then we can move forward. All right, so let me stop this. Start this once again. Every time I unshare my PowerPoint once, then Zoom gets angry, and then next time I'm trying to reshare, then it doesn't show me easily. Maybe this is the one. Do you see my screen with slides now?
No.
No. Okay. Okay. Let me figure out. Sorry about that. Towards the tail end of the pandemic, one would have thought that I would know how this Zoom sharing works. Okay, I got it. All right. So, like this is the slide that is making the, reinforcing the point that I was saying, that control logic dictates the consistency requirement. And this is completely up to the programmer, right? So the control program has to make a judgment call about what type of, requirements it has for a particular network state, right? And it can say that I want it, I want to make sure that it is consistent and replicated across different instances, or I am fine using these type of transient storage services, so that I can bear with some type of inconsistency in the data. So overall, I think Onyx was a great system because it was a production system that instantiated the concept of distributed state abstraction that SDN really embraced and talked about. It was a very complicated system that was evolved and developed over multiple number of years. I think the main idea started in 2009-10, and then this research paper was published a couple of years later. It does offer some really good things if you're an application developer writing control programs, but at the same time, it just left a scope of significant improvement, because the most important thing was that it left a lot for the application developers to reason about these, the resolution, the consistency issues, and reason about how are we going to resolve conflicts if there are two different, entities trying to access a particular network state at the same time, and there is inconsistent view. So how do you handle that inconsistency? So these are all these things that it provided a better abstraction, but it still that better abstraction was not as envisioned, right? It left a scope of doing so much better, right? But I would say, like, one of the biggest challenge that the community faced with Onyx was that even though it started, absorbing whatever was in the open source community and trying to adapt that into practice, it wasn't really open sourced, right? Onyx per se was not open sourced. And, like, there might be a lot of business reasons. I can't comment on that, but whatever were the business reasons, Onyx was not made open source, which meant that, like, researchers can't really experiment with it. Clearly, Onyx left a lot of, gap between what is desired and what is required. But not having access to that in the public domain just made it much difficult to just use Onyx as is and then innovate. So this motivated the design of a new system, and something which, like, now we know is something quite popular. It is called ONOS, and it was, like, the keyword here is Open Network Operating System. And before I talk more about the specifics of ONOS, like, open networking, like, there is this entity called Open Networking Foundation, and there were a couple of other open source, like, communities that were created around that time. And I think, like, they basically did a fantastic job channelizing all the energy that people had around software defined networking into open source software, right? The reason that this community was able to grow significantly was that a lot of artifacts were out there in public, transparently available, and everybody could look at that. And the initial prototypes, everybody could actually criticize them and say, like, hey, this sucks, right? Because, it does not support X, it does not support Y. But at the same time, at least those artifacts were out there in public, and researchers were able to, like, identify problems and limitations of these solutions and contribute back to these systems, to these open source systems. And eventually these systems have matured. I won't say it's a, like, grand success that, everybody is just using ONOS, but it is definitely a very strong alternative that a lot of enterprises, a lot of companies are considering or are already adopting in their network, because it is actively maintained, and it is, like, all its flaws and, good features are known publicly in the community, right? So this is kind of like one of the most successful project that was run by the Open Networking Foundation, right? And I think, like, the community is reaping a lot of benefits out of that open society. So as I said, right, I think there are a lot of building blocks that were already available in the distributed, like, distributed systems community, right? So the problem that the networking community had to solve was to figure out that, like, what is very specific about networking that they have to take into consideration, or, like, come up with a custom solution for those specific problems. And what are the set of problems designing these network operating systems that can be just simply offloaded to the existing distributed systems, right? So ONOS basically tried to do a better job of coming up with even better set of abstractions and data models that facilitated bridging this gap between the networking requirements, and the requirements of, like, offerings of the distributed system. So it tried to bridge the gap, right? So what are the existing implementations? We talked about storage being a requirement, that we want to have this storage, like, which is the storage for the network information itself, which enable the network information base and getting, like, making sure that it is the one that is accessible to control program and has all these consistency requirements as well. So distributed storage was definitely a requirement, and there were already very successful and widespread, like, widely used distributed systems out there, right? So now these names might not ring a bell, but 2015, 2016, everybody was talking about Cassandra being such a nice solution for distributed storage. RAM Cloud, maybe not that popular, but I think RAM Cloud was very attractive because of its simplicity and kind of, like, the offerings, like, the transparent offerings that it provided. And then there were a lot of systems out there that were trying to do distributed graph, right? So like providing this distributed graph database, right? So Titan was one example, but now we know that there are so many other distributed graph databases out there where you can, like, have these multiple or different instances run a subset of, like, or store a subset of the graph, and you can query that distributed system to get answers which you will get in as, like, from any centralized graph database, right? So Titan was one example. And then there is this notion of distributed event notification, right? So as we know that in networking, it's all about notification of events so that the control programs can react to it. So like either you implement something from scratch on your own, but in the distributed community, the distributed event notification, there were already very successful systems out there, right? And same goes with the coordination system as well, right? So where is coordination required here, right? So what type of distributed coordination are we talking about? Can anybody give me an example here? That what is the distributed coordination in context of the network operating system? Okay, load balance. Yes, that's a good thought. But load balance for what? Is that, are you thinking of load balancing as an application? Okay, so I think maybe I can try to answer this question. Like from the network operating system perspective, the requirement is that now we have these different instances, right? So what type of mapping should we have between the switches and these, ONIX or ONOS instances? Should we have one-to-one mapping between switches and these servers, or should we have many-to-one or one-to-many, right? So what are your thoughts? Like, what do you think that should a switch be just connected to one server? Should it be connected to multiple servers? Or what can be an alternative here? So yeah, I think many-to-one we definitely have. So, okay, let me refine this question because maybe I've confused you. So we have, like, consider 3 switches, or maybe I should use the visualizer so that it gets easy for the discussion. Okay, you can see my notebook, right? So as I said, like, we'll have this example. You have a bunch of switches in the network, right? And you have an instance, and you have another instance, and bunch of more switches, right? Now, what will be an example of one-to-one mapping? Can anyone tell me? One switch per server, exactly, right? So one-to-one mapping can be that we have one switch per server, right? And everybody has a dedicated connection, right? But as you can imagine, that's going to be very expensive if you have a lot of switches in the network, right? So that's not very desirable. So if that is not desirable, what is a desirable situation? Many to one, right? So many to one, what does that mean? That we have a bunch of switches, a bunch of servers, and right. So this, like, many to one, right? This is the setup that we are talking about. Now, tell me, is this a desirable situation? What happens if this instance of ONIX or ONOS goes down? What will happen? Yeah, you lose all the information. Basically, like, for the nib or the control program that is sitting at the top, if this ONIX instance goes down, then it has no way of reading state from these devices or writing state back to these devices, right? It basically has no way of communicating because these devices, these switches were only talking to just one server, and that one server just failed, right? So to provide resilience to these type of failures, rather than having many to one, the approach is to have many to many, right? So these switches like not only connect to one, server one, but they will also connect to server two, and same for the other set of switches as well. So now when they're connected to these two set of servers, then which server should they be using for communicating information, or which server should they be expecting the information to be coming from, right? So that is kind of like a question from the design perspective. And this is a very standard distributed systems problem. What you just do is that you have this type of setup and you just select a leader, right? So these switches select a leader that, okay, switch 1 is our leader. And these set of switches decide that, okay, server 1 is our leader, and this will decide that server 2 is our leader, right? So this is a leader election problem, right? And this is where some type of coordination is required between these entities. And that's where, like these solutions like Zookeeper are desired, because they will facilitate leader selection. So when everything is fine, then server 1 is the leader for all these 3 set of switches that we have in here. And when it fails, then like server 2 can actually become the leader, and then they can start communicating with server 2 for most of the important tasks, right? So I'm just giving an example with 2 servers, but like there are multiple servers that each of these switches will maintain connections to, right? And at any time instance, there will be only one of those servers that will be the leader. And the selection of which server is going to be the leader is coming through these coordination protocols, or like distributed coordination that is required. And Zookeeper is one such software solution that is providing this coordination among the switches and the servers. Okay, is this concept clear? Perfect. All right, so I'm going to try this again. Hopefully I can find that Microsoft PowerPoint sooner. Yeah, it should have some intelligence embedded in it, where it should know that what type of screens I've been sharing. So rather than dismissing it completely, it helps me find that. Yeah, now. Oh, I got it. Okay. Okay. All right. So I think one thing that also is worth mentioning here is that like these are the building blocks that ONOS used, but ONOS, like the version that we're talking about right now, was actually like proposed in 2016, and the area of distributed systems has grown tremendously since then, and so has the ONOS, right? So like whatever we are learning here in terms of the software stack or software solution that were used as part of this initial prototype of ONOS, like that don't take it as this like that's the only way ONOS can be implemented. Like what is more important is that it was able to map these different phenomena that we have already, or like different distributed system requirements that we have from a network operating system, and was able to interface existing software stack to make it work, right? And of course, like the first iteration that they came up with was not very efficient, because just plugging in different open source tools to make things work is not the most efficient way of doing things. But at least it got some network operating system instance out there, and then over time they iterated. And the one that we are looking at right now is the improved version of ONOS, but not the final version of ONOS, right? So how like what is the architecture here? The architecture here is that it is using a very popular at that time it was using this popular open flow manager called Floodlight. And Floodlight was popular because it was commercially like maintained. There were like a proper organization that was responsible for maintaining Floodlight controller. So like they just use that open source realization to implement this bottom layer, and you can think of that as the southbound API for this network operating system, right? And then they use the distributed key value store, and they use an instance or like software stack called RAM Cloud to implement that. And on top of that, they were providing this ONOS graph abstraction, which is basically extracting the information from this key value store to provide this, network view to the control programs or control applications. and then like, it exposed a particular certain API, and then the applications were just interfacing with this graph abstraction that it was offering, right? And to maintain this coordination between the servers and switches, it was using Zookeeper to make sure that like everyone knows who the leader is for a set of switches. And like for notification, like for handling events, it was using a tool called Hazelcast. I don't know much about Hazelcast. It wasn't really that popular around the time when I was learning about it, but I think I am pretty sure that the ONOS current implementation is not using Hazelcast, right? So the abstraction that ONOS was offering was not very different from Onyx, right? So Onyx was also offering similar abstraction that you can, like visualize. You can have a network graph, which is, like giving you exposure to individual network entities such as switch, port, link, host. And then there were some new ideas that were introduced, which are like, flow path. I think like the most interesting thing was that it was providing this abstraction for path itself, where you can reason about, or you can try to directly access the state of a path, right? So what do we mean by the path? I'm not going to switch to the visualizer again, but I think like, we had that topology with 6 switches, right? So if I'm going to go from one end to the other, I have 2 possible paths. I can go from the upper set of switches, or I can go from the bottom set of switches, right? And like the Onyx way of looking at these network graphs was that if I want to learn something about the top path versus the bottom path, then I have to first figure out that what were the switches that were part of this path at the application layer itself, right? And then query them individually, and then figure out, okay, what is the state of this path, right? So in contrast to that, what ONOS was offering was that it was offering a path abstraction itself, right? So you can actually directly query path as an application itself. So in some sense, it is, like just another higher level of abstraction that is exposing, so that you don't have to do the low level. Like when I say you, I mean the application developers, right? So the application developers don't have to do the low level processing themselves. They can just query a path and say like, okay, which link in this path is most congested, right? If that is the question that they're looking for. So then they can just query this path attributes and figure out which link is most congested for this path. So this is something, like a new abstraction, a better abstraction that ONOS was able to offer. So in summary, I think, ONOS builds up on Onyx. Onyx was something which is kind of like the building block here. But Onyx, as I said, because it was not open source and publicly available, so it was really, really hard to innovate in the space. And that motivated the design of ONOS. It instantiates the desired global view at scale. And the biggest contribution of ONOS, I would say, is that it leverages the existing distributed system techniques and implements them in context of a network operating system, and then figures out how to solve the scalability and reliability issues, right? So rather than trying to design some new custom distributed system only for network operating system, I think that is not something which is a very sustainable approach, right? Like a better approach is that, okay, this is a distributed systems problem, right? Let's try to map the requirements of a network operating system to what is offered by the distributed systems, right? And then just use off-the-shelf existing software stack to build this network operating system. I think like this is very smart. And like if you have to do something in the future, like that's the first thing that you should do, right? Trying to come up with a completely clean slate idea or clean slate implementation, and starting from everything from scratch, there is a lot of risk in such an approach, because then you have to like replicate doing things that people have already done, right? And that's just waste of your production cycles. And that is what the community was trying to figure out as well, right? So 2014, 2015, when ONOS came out, there was a lot of chaos in the networking community, right? Nobody really understood that what really is a controller, what really is an operating system in context of networking. People were always confusing controllers with network operating system. And as I was showing here, that open flow manager, which is the floodlight and Ryu and Nox, and but there were a bunch of others open flow managers that were created. whose job was to provide, say, a Python interface for writing, open flow rules into the data plane, right? But that is not an operating system per se, right? It's not really offering you a consistent view or a logically centralized view of the network. And that is the most important thing to qualify as a network operating system. But that was, like, as I said earlier in my earlier classes and earlier lectures as well, that now in retrospective, it is really easy to put things into perspective and say, like, oh yes, we needed this abstraction and we needed this realization for that abstraction. But I don't think that's how the evolution of these ideas happened in the community. We just learn things as we progress, and we realize that like whatever abstractions we have right now are not good enough to move forward. And now we need this distributed state abstraction. Now we need some other abstraction, virtualization abstraction, as we will or the specification abstraction specifically. So there are these different abstractions that evolved and came with time. And like 2014, 2015, there was a lot of chaos in the community. There were a lot of research groups or practitioners who were trying to build network operating system from scratch. ONOS was very smart in that perspective. I'll give them all the credit that it deserves here, that they just figured out that most of the problems in the network operating systems are mapped. One can map them to the existing distributed systems. And then the problem of building network operating system is to just find the right mappings, right? And as evident from their evolution itself, that the first iteration that they came up with were not really the most effective ones, right? So they eventually used some other graph abstraction, but the first one that they used was something called Titan. And Titan was like a graph database, distributed graph database service software that was kind of like publicly available, but then it didn't really offer the insights that were really required for networking. So this is kind of like hit and try or evolutionary process, that you start with something and then you realize that okay, it's not really working, and then they kept evolving. So as we proceed further in this class, like we'll be learning a bit more about the ONOS, and sorry, as part of the programming assignments as well. So the third programming assignment will be focusing on writing application for the the application of the control program for the ONOS framework, right? So we'll be learning more about ONOS as we proceed, but right now I'm just trying to give you like where is the design spectrum ONOS is lying, right? And how is it different from ONIX? What were the fundamental questions that ONIX answered, and what problems it just left unanswered? So how did ONOS really fill the gap? So these are the things that we should try to understand right now, but we will be digging a bit more deeper in the discussion section on the ONOS and try to understand that like what different components are there right now, and like how can we write a new like STN program or a control program on top of ONOS, right? So what really is exposed to the program, and how exactly we can write those programs, okay? And also to put things into perspective here, that with reference to the PISA switches, right? So now you might be looking at this figure and you think like, where does PISA switch comes into the picture, right? So how like, do you like, is this architecture something that you think is, flexible enough to accommodate different type of targets? Where do you think like PISA switches will come into the picture here? So let me try to be a bit more clear here. What we are trying to learn here is the network operating system, right? What we are looking at in this architecture is a specific instantiation of a network operating system. Now, like as we learned before, that the communication between the network operating system and the data plane target happens through southbound APIs, right? OpenFlow is an instantiation of this flow space abstraction or like the forwarding abstraction, right? But the PISA switches are also data plane targets that are programmable, that have their own forwarding abstraction, which is not very like the forwarding abstraction offered by PISA switches, forwarding abstraction offered by OpenFlow switches is very similar. They require match action table entries, right? So in some sense, you can think of them having the match action table abstraction, right? So in context of ONOS, originally when ONOS was designed, pizza switches didn't exist, right? So now how is this going to work where half of the switches are open flow, half of the switches are pizza switches, right? How is this going to interoperate with each other? So that's where I think, like the flexibility of these southbound APIs is important, right? So like, the network operating system is not or should not be designed such that it is, strongly coupled with a certain type of southbound APIs, right? So the flexibility, that the software stack or the architecture should be flexible enough such that it can accommodate different type of southbound APIs here. OpenFlow is just one instance. Whatever is the interface for pizza is the other, right? So P4 runtime is what we were like learning in the last set of lectures. That P4 runtime is kind of like the southbound API in that context, right? Or maybe I'll take that back. So I'm not 100% sure if P4 runtime is the right abstraction to think about the southbound APIs. I think like we'll cover that in the next lecture. I'm not 100% sure what is the right term for that, but point being that it's not open flow, right? So not everybody is just using open flow entries to program the entries in the pizza switches, and which means that you need a specific set of drivers in the network operating system that can interface with these new set of targets, right? And pizza is just one type of target. Open flow is just one type of target. You really want to make sure that these network operating systems are able to interface with all different types of data plane targets in the network, which means that there should be some flexibility in terms of what type of drivers they are supporting for the southbound APIs, right? So that is just one example, and we will learn that how exactly the ONOS has evolved and how exactly it supports the P4 or PISA targets in the next set of lectures. Okay. All right, so this brings us to the end of the of this like module as well as the class. That the network operating systems are instantiation of software-defined networking's distributed state abstraction, right? And like this point is very important to understand that I can like the controllers like say Ryu or Floodlight or Open, like the ODLs, all these type of controllers that were designed, they were not really network operating system, for the reason that they were not really offering the distributed state abstraction, right? A lot of them were not really offering the distributed state abstraction. There was no definition or no notion of network information base or the network graph that is getting exposed to the control programs, right? So, like it gets very easy to confuse the controllers and network operating systems, but like the biggest requirement for network operating, for any software to be a network operating system, it should offer or it should realize this distributed state abstraction. If it is not doing it, it's not a network operating system. Okay. And by design, scaling these systems is non-trivial, right? And what I mean by design, because as we were discussing, that there will be some state that will get updated at the rate at which the packets are coming in, and that's extremely high rate of change, right? So there is a lot of dynamism that these network operating systems have to deal with, and that leads to scalability challenges. And we talked about different techniques that have been embraced by different type of offerings for network operating system. Most of them have converged to be distributed because it's not really possible to have one centralized operating system for a production network. You have to distribute that. Now distribution can be flat, right? So without any notion of hierarchy or something, it can be just simply flat, that bunch of switches connect to one server as their leader, right? And it can be that flat hierarchy, or it can be like it can leverage this natural hierarchy that is there in the networks that say there are these one set of instance that is connected to n switches, and then those instances are connected to another set of instance which is grouping these different set of devices, right? So a very simple way of thinking about it is that in context of say network data centers, then there one top of rack switch, right, which is like basically connecting all these servers or OBSs in that rack is connected to the top of rack switch, right? So this top of rack switch can connect to one controller, and then this one controller can connect to another controller which is having all the top of rack switches in that data center, right? And then they can further connect to all the other ones that are representing the bunch of top of rack switches on other data centers, right? So there is a natural hierarchy that exists in the networking, and that is what some of these proposed hierarchical like operating system were trying to capture and leverage. And the other notion that we tried to cover briefly was the offloaded, where we can offload some of the tasks to the CPU that is sitting on the switch switch itself, right? So switch has a small CPU, not very capable, but you can offload some of the control tasks to that switch to improve the scalability of these systems, right? And we also talked about the fact that when you build these type of distributed systems, then you have to address these issues about reliability, consistency, and like performance, right? So when I say performance, basically like there is this natural trade-off between consistency that you can offer versus how fast you can do that, right? So we talked about this abstraction or different notion that different states that are related or that are of interest for the network operating system have completely different set of requirements, and that provides an opportunity to address this balance between the consistency and scale, right? So like there are certain set of states that needs to be replicated, but they're changing slowly. So those are offered through replicated storage, and then there are other set of states that are very transient, very volatile, and you can't really ensure this replicated storage for them. So they use distributed hash tables to realize those type of network state, right? So I think like that brings us to the end of network operating system. And as we like the progress that we have made so far is that first we tried to understand software-defined networking as a whole. Then we started bottom up. So we started learning about the data plane targets. We learned about the software switches. We learned about the hardware switches. Now we have progressed to the network operating system, and we have completed that. The next step for us is to understand the network virtualization concept, right? So how network virtualization layer, which sits on the top of the network operating system, just realizes the specification abstraction that is key for SDN, and how that simplifies things, and like how that was a game changer in making software-defined networking a really important and commercially important solution out there. Okay, so with that we can end today's lecture, and of course if you have questions, feel free to ask me over Slack, but I will highly encourage you to come to office hours or discussion sections. All right, thank you all. Cheers.